And the first one on my list comes from the University of New Mexico. Jawad, are you there?
Yes, I am here.
All right. Would you like to share your screen?
Absolutely.
What a beautiful backdrop. Are you outside?
Oh, I wish, but that's that's just the university.
All right, you take control.
All right, all right. All right. Can everyone see that?
Yes, it's very good.
Okay, perfect, perfect. All right, so hello everyone. My name is Jawad Musa. I am a PhD student at the University of New Mexico. I work under Dr. Anil Prinja, and I have been on this project since the beginning of this year and a little late last year as well. And today I'm going to be presenting on neutron multiplicity distributions using stochastic and deterministic solution methods. So to start off, first of all, I want to take a moment to talk about neutron multiplicity counting and how it relates to the work that we're doing and NNSA's mission. So basically, neutron multiplicity counting has been widely used in nuclear safeguard due to its benefits in identifying special nuclear material. It basically provides unique signatures that allow for the identification of these specific materials. And the goal of this project is to develop a hierarchy of deterministic solutions, starting basically from a point model and working up to higher fidelity. These modeling and simulation techniques are going to provide basically they're going to complement experiments and provide predictive capabilities. So if you take a look at the image on the right here, what that shows is a neutron multiplicity distribution for the number of counts. And I think that this is a very descriptive image when it comes to talking about neutron multiplicity counting and what it really entails. So it's based on observing statistical fluctuations of the emitted neutrons. So if you take a look at the red and green lines to begin with, the red is a single fission event that is not allowed to multiply, while the green line is a single event that further multiplication is allowed after that. Now, if you take that green line and you normalize it to a Poisson with the same mean number of neutrons, you can see how on the tail it starts to deviate from a Poisson distribution. Analysis of that deviation is what really provides insight into what the special nuclear material may be. So we started off with a point kinetic model, and we developed that and to solve for the probability distribution of neutron counts. And in particular, the quantity of interest that we focused on was the Feynman-Y. And I'll talk a little more about what that is here in a minute. But we used Monte Carlo methods and deterministic solutions to achieve that. So how does that relate to the NNSA's mission? And basically, advances in modeling and simulation will support nuclear material detection. And not only will they support nuclear material detection, but also making these the theory and the computational modeling available to the nuclear security community will encourage further development on the experimental side and so on. And last but not least, educating and training future experts, hopefully like myself in this field, to go on and hopefully do great things in the future and have a very good understanding of what the nuclear safeguard entails and how we can make this world a better place. So the first thing we wanted to do is we wanted to tackle the Monte Carlo approach. And in order to do that, we had to take a look at the system from a fundamental standpoint and really break it down to an event-by-event basis. So what we did is we started by conducting a probability balance of all independent and mutually exclusive events that a neutron can undergo in a specific time period. Developing this probability balance is a step towards deriving what's known as the forward master equation. Now, from that probability balance, we developed a algorithm, which is known as the stochastic simulation algorithm. And not by any means were we the first ones to develop this, the theory behind this algorithm, but it's definitely the first time it's been applied to this space and using it to look at the neutron counts for the purpose of nuclear safeguards. Now, what this algorithm does is it basically simulates the state of the system in concert, where you're not following each event by event basis like traditional Monte Carlo, but in a sense, you're just stepping through time and changing the state of the system all at once. You can see table 1 kind of illustrates what I'm referring to, where if you have, for example, a spontaneous fission event, what you do is you change the number of neutrons by whatever number of neutrons were produced during that event. And you can see that the state of the system can be defined to be whatever it is, whatever quantity of interest or you're looking to track is what you can define the state of the system to be as. For our case, we took the neutron number and the number of counts. This algorithm proved to be very efficient when it came to modeling point kinetic systems, and especially at subcritical systems, due to the fact that there aren't many neutrons in the system, so the population never grows large enough to shrink your time step. And we wanted to test it, so we used it to reproduce some results that were previously published, and that you can see there on the right in figure number 2, where we have a 80% Pu-239, 20% Pu-240 sphere at 3 different masses. And you can see that as the mass increases, the deviation from a Poisson or the single spontaneous increases, which is an indication of increased multiplicity. Now, Monte Carlo simulations are very powerful, and they've been used for a very long time due to their simplicity and accuracy. But if you've ran any codes in the past that relied on Monte Carlo techniques, one major challenge is they require a very long runtime to achieve accurate results. On the other hand, deterministic methods provide orders of magnitude of speed up potential. Of course, the price you pay is they're a little harder to get to initially. However, that's what led us to work on developing what's known as the backward master equation for the number of neutron counts in effort to achieve a deterministic solution. So just like the forward master equation that we talked a little about previously, this equation is formulated by conducting a probability balance of all independent and mutually exclusive events, just like the probability balance on the previous slide. However, the main difference is the probability balance is conducted in the first collision interval. So that leads to 2 probability distributions that need to be defined. The probability of n neutrons leaking from the system by time t, given that 1 neutron was introduced at an earlier time s, and the probability of n neutrons leaking from the system at time t, given that an intrinsic random source is turned on at an earlier time s. And the reason these 2 had to be defined independently is because the ultimate goal of the project is to obtain the count distribution in a given detector time gate. And in order for us to achieve that, two problems had to be solved. One was starting with an initial neutron in a fixed time interval, and after that, you're able to solve the intrinsic random source count distribution in a fixed time interval, since it depends on the solution for a single chain count distribution. So down here, I won't go too much in detail. I won't bore you with the math behind the backward equation, but I do want to take a moment to walk you through what it really represents to present the complexity and the nonlinearity that gets introduced when looking at the system using the backward approach. So if you take a look at the single chain equation, you can see that the first term basically gets introduced from the probability of no event. And then you have the event of a capture event occurring, which only contributes if the final state of the system is 0. And then we have the leakage probability, which in order to specify specific time gate, we have to introduce then an indicator function, which basically says that if the time gate exists after while the neutron is in the system, then it can be counted. But if the time gate is outside of that time, then it doesn't count. And last but not least is the fission event. And that's what really introduces the nonlinearity, where you can see how you have to follow each individual chain in order to ensure that they collectively produce n neutrons at the end of the simulation. So, yes.
Do you have a pointer that you could use?
Oh, yeah. Can you see my mouse?
Yes, maybe that would be helpful as you're describing the equations.
Yes, yes. I apologize. So just a quick recap. This is the term that I was referring to from the non-event, the capture, the leakage, and this is the fission term right here. Now, this equation must be identified first, because as you can see that for the random intrinsic source, this equation does depend on the solution to the single chain equation above. Now, what we wanted to do, the first thing we did after writing these equations down is we restricted our physics to benchmark the SSA algorithm to a binary fission model. Now, we refer to it as a generalized binary fission model because we define the probability of n neutrons being produced is 0 for n greater than 2, which means that you can produce 0, 1, or 2 neutrons, but nothing more. So we were able to obtain a steady state solution, an analytical solution to that equation, and that's what's given right here. And the plot on the right illustrates the results for all three different masses compared with the SSA algorithm. And you can see that they match fairly closely until you get down to about a probability of 10 to the negative 8, which is very small. So I would say that these are very accurate. Now, the challenge with the analytical solutions is that they're not always solvable. So some tools mathematical tools need to be introduced to help achieve a solution or even obtain information from these equations without having to solve them. And that's where a generating function equation comes in. And for those who aren't familiar with what a generating function is, this is a quote that I believe sums it up perfectly, where a generating function is a device somewhat similar to a bag. Instead of carrying many little objects detachedly, which could be embarrassing, we put them all in a bag, and then we have only one object to carry, the bag. So in this case, you have an infinite number of equations that represent the probability of the probability distribution, and a generating function transformation truncates that, reduces that infinite number of equations into a single PDE, which is what you see here. So we applied that transformation to both equations for the single chain and the intrinsic source as well. The strength of this method comes when you start taking moments of these equations. Now, since the generating function equation is not always solvable, one important thing to note is that taking derivatives of these equations and setting z equal to 1 is equivalent to the moments of the probability distribution. So now we can obtain the mean number of counts or the variance of the counts without having to solve the equation at all, but by simply taking moments. So you can see here that the first moment is equivalent to the mean number of neutrons, and the second moment is equivalent to the second factorial. And with these two, you can obtain the variance and standard deviation, and so on. And that's what leads us to the Feynman-Y, which is defined as the ratio of the count distribution's variance to its mean. So we were able to solve those equations analytically for the first two moments, and we obtained an analytical solution to the count distribution's variance and its mean, and we were able to implement this. Now, before we get into some results, I want to make sure that we make a connection of how the Feynman-Y relates to nuclear safeguards. And it's considered a very important quantity in identifying special nuclear material because it's a measure of the system's multiplication. So it basically represents the excess variance as a deviation from a purely uncorrelated Poisson. So you can see that as the distribution becomes more Poisson-like, the Y disappears. However, as at larger time gates, or as we propagate through time, it loses its time independence, and it becomes a given value that we can use to characterize that system. This plot here on the right was taken from a paper published by Mattingly at Sandia National Labs, where it represents the Feynman-Y, which is typically plotted against gate width in microseconds. That's the gate width of the measurement times for the Lano-Burt ball with a polyreflector. And you can see that it grows initially, and then it plateaus at a value a little above 1. So we wanted to produce similar results for the plutonium sphere that we've been working with, and that's referenced in many previous papers. And what we did is we took the three masses that were previously used for the 80% Pu-239 and 20% Pu-240, and we were able to get point kinetic parameters by running a detailed transport calculation of the problem. And we compared that with the published parameters as well that were previously published to make sure that they're aligned. And what you see plotted here is the Feynman-Y for two masses. And you can see how it grows at a similar shape as the plot before, and it matches pretty much actually almost exact with the SSA algorithm that we used, which is a Monte Carlo. So here we have a comparison between both Monte Carlo and a deterministic solution where we were able to obtain the Feynman-Y parameter. Now, we want to be sure to simulate how this value is produced on the experimental side. Now, what we've been working with so far is just the math part of it and the moments. And we want to see if we can get it to match the same value if it was to be produced the way a neutron multiplicity counter would produce it. So to give a little background on how that works, and I want to take a moment to thank Justin Hutchinson on helping us understanding this technique at Los Alamos National Labs. Basically, a neutron multiplicity counter detects neutrons emitted from a system. And when it's operated in list mode, you end up with a a list of neutron pulses basically detected at different times. A bunching method is used after that, where that time history is broken up into smaller time gates. And you check how many neutrons were detected in each gate, and that gate gets bigger and bigger and bigger, and the same process is followed throughout. Now, once you have a multiplicity distribution of these counts, the variance to mean of all time gates is produced, and that is what you see plotted as the Feynman-Y against gate width. So we took a similar approach, and we wanted to see if there was a difference between generating a time evolution of y from time 0 to a given time versus measuring the Feynman-Y in specific gates at a later time in the future. And you can see that we saw no difference in this plot here on the right, where the histogram-like line represents the Feynman-Y within given specific time intervals, while the continuous line is the time evolution, and you can see that they match exactly.
Well, you need to finish up pretty soon.
Yes, yes. So that is actually takes us to the impact of this work, which is going to provide a deeper understanding of the statistical uncertainties of radiation signals. And we're hoping to provide a deterministic alternative to expensive Monte Carlo simulations. And what MTV has impacted this work is it helped us create a link between the partners at the university and national labs, and allowed us to be part of training seminars and very informative sessions that really helped expand this work. And with that, I just want to conclude that we found the SSA method to be very efficient for simulation of point models, and forward and backward equations were provided a very efficient deterministic option for computing count statistics, and advancing modeling and simulation capabilities will help the nuclear security area in support of the NSA mission. So with that, I would like to thank MTV and Jessen for tying the connection to the experimental side, and we hope to work more with Jessen to reproduce the Feynman-Y by developing codes to simulate the NPOD here on the right, and add spatial dependence to start looking at the Lamel-Burt ball, which is the image you see here on the below. And I'd like to thank NNSA and DOE for making this work possible, and all the MTV partners for your support and your attention. Thank you.
Excellent. Thank you, Jawad.
Absolutely.
The floor is open for questions. Anybody?
I apologize. I know I went over by a few minutes, but thank you for your patience.
Questions for Jawad?
Hey, Jawad. Nice question. This is Michael Hua. Hopefully you can hear me.
Yes, yes. Hi, Michael.
Cool. So nice presentation. I'm definitely interested in the results, knowing when to use the point kinetic model and when to use something more complex. So you, in your intro on motivation, you say that you develop, I guess, this other method, and I don't have my literature in front of me, but how does your derivation of your PN differ from, I guess, prior works, or like Imre Pezit and Leonard Paul's book?
One major difference between the work that we've done and other work done in this area is that we're looking at external counts when all equations have been developed for the neutron population and the number of counts within the system. So that's one major difference there.
Other questions? I got a question for you, Jawad.
Yes, please.
Can you move to like a 1.5D solution to the problem rather than a full 2D is out of the question, but what about 1.5?
So part of our next steps for this work is we want to add spatial dependence and energy dependence. So that's definitely in the future plans for this work.
Once you start to move to spatial and time dependence, aren't you going to suffer relative to Monte Carlo?
Well, so that's what we're hoping to provide. Of course, there's going to be challenges there, and you know, achieving a deterministic solution is going to be a little more complex. But we're hoping to introduce new methods that that might make it a little more efficient to obtain the values, specific values of interest, instead of having to simulate the entire system and then extract what you want from it. So there's definitely a trade-off.
Okay, any other questions? All right, one final question, Jawad. You're solving the forward problem in
Yes.
saying I've got this configuration and I will get these answers at the end. But the problem is usually when I measure these measurements, what was the initial condition, the backward condition? Can you talk about the mapping from the backward state to the forward state?
So if I understand you correctly, what you're asking is that with the backward state, that's not how reality is. It's more of in a forward approach. And your question is, how do you go from backwards to forward?
Sure, if I give you a set of measurements, what can you tell me about the initial state?
I see. So we haven't really looked too much into analyzing current measurements, but more of producing multiplicity distributions using a deterministic method. And I hope that answers your question, because I think what you're referring to is I'm out in the field and I detected a bunch of measurements. I have measurements. How do you post-process this to gain knowledge about the sample? And that is something that we haven't looked into.
Ah, but you've only got 4 more years to solve that problem, Jawad.
There you go.
All right, well, we're going to give a virtual clap to that lovely presentation, Jawad. It was wonderful.
Well,
thank you so much. I think we all learned a lot from it.
Thank you. I hope so.